x, y, and z are complex numbers such that x plus y plus z equals 1, x squared plus y squared plus z squared equals 2, and x cubed plus y cubed plus z cubed equals 3, what is x to the fourth plus y to the fourth plus z to the fourth? No, it's not 4, although that would be awfully convenient. Give this problem a shot. It's not as simple as it looks.
Before getting started, I should mention that this video is about a lot more than just solving systems of equations. By solving these systems, we'll be building up to a beautiful theorem called the fundamental theorem of symmetric polynomials, which we'll prove at the end of the video. If that sounds interesting, stick around to the end.
With that said, let's get to solving. A reasonable first step would be to do what you would do with any system of equations. Isolate the variables one at a time, and solve for each one of them individually. Maybe we start by isolating y in the first equation, so we have y equals 1 minus x minus z. Then we plug this value of y into the second equation to get an expression that just depends on x and z. Next, we want to solve this equation for x. If we think of z as a constant, this is simply a quadratic equation in x, which can be solved like any other quadratic. We first expand the middle term. Now we combine like terms to get 2x squared plus 2xz minus 2x plus 2z squared minus 2z plus 1 equals 2.
Okay, bear with me because we're going to do some things that are far from elegant, but I promise I'll make it as painless as possible, and it will all be worth it when I show you the more elegant way. We have this quadratic equation in x, so let's use the quadratic formula. We need to put it into standard form, ax squared plus bx plus c equals 0, where a, b, and c don't depend on x. We can do this by subtracting the 2 to the other side and factoring to obtain 2x squared plus 2z minus 2x plus 2z squared minus 2z minus 1 equals 0. In this equation, a is 2, b is 2z minus 2, and c is 2z squared minus 2z minus 1. Finally, we can apply the quadratic formula. That gives us this nasty expression for x in terms of z. Now, we'll revisit the expression we had for y, and plug in our expression for x to get an expression for y in terms of z. Remember I said things were going to get messy?
At last, we have x just in terms of z, and we have y just in terms of z. So we can plug these two expressions into the third equation to get this beast. This equation is nice because it only contains z, but it's terribly complicated. Well, you know what we have to do. Simplify. To spare you that headache, I'll do it quickly on screen. Nothing clever is going on here. I'm just multiplying things out and combining like terms where possible. Don't worry about following the algebra if it's not your cup of tea. Whoa, we ended up with something pretty simple. 6z cubed minus 6z squared minus 3z minus 1 equals 0. The formula looks like this. Yikes, that's pretty messy. I certainly don't want to go through that headache. And even if we were to successfully apply that formula, we still wouldn't be done. We'd have to plug the value we get for z back to find x and y, and then raise all three variables to the fourth power and add them to compute x to the fourth plus y to the fourth plus z to the fourth. So while this new equation seems helpful, solving for z explicitly is not a good next step.
So what else can we do? The astute among you may have realized something when we set out to solve the problem. Our choice of which variable to solve for in which order was completely arbitrary. Instead of isolating y in the first equation, we could have isolated z to get z equals 1 minus x minus y. Then we could have plugged this value of z into the second equation to get an equation just in terms of x and y, and solve this equation for y in terms of x. But remember this equation we had before with x and z? It's essentially the same thing, just with the variables switched around. That means the solution we'd get for y would be the same as what we got for x before, just with an x instead of a z. And finally, if we had used this to substitute for y in the first equation and then eliminated y and z in the third equation to get an equation just involving x, we'd end up with essentially the same monster equation we had earlier. So, doing the analogous simplification steps, we'd end up with the exact same polynomial, just with an x instead of a z. 6x cubed minus 6x squared minus 3x minus 1 equals 0. And I bet you could see how we'd get the same thing, but with y instead. These three equations imply that x, y, and z are all roots of the polynomial 6t cubed minus 6t squared minus 3t minus 1.
The whole reason this works is because in each of the given equations, all three variables play the same role. They're all added together in the first equation, they're all squared and added together in the second equation, and they're all cubed and added together in the third equation. That means if we do some procedure to derive a fact about one of the variables, such as finding that z is a root of some polynomial, we can do the same procedure with the other variables to derive that same fact about them. All the variables must be a root of the same polynomial.
A mathematically precise way of expressing the idea that all the variables play the same role is as follows. Suppose we define three multivariable functions, f, g, and h, based on the given equations. These functions have the property that it doesn't matter what order you plug the inputs in. For instance, f of xyz is the same as f of zxy because x plus y plus z equals z plus x plus y, no matter what x, y, and z are. We can say something similar for g and h. In fact, any ordering of the three variables yields the same result. A mathematician would say that f, g, and h are symmetric.
So how does the fact that the given equations are symmetric help us? Well, we've already used the symmetry to conclude that since this is true, these other two equations must be true. Remember our goal. We're trying to figure out what x to the fourth plus y to the fourth plus z to the fourth is. Pause and see if you can use these three equations and the given equations to solve the problem in a slick way. Here's something you may have tried. Since we want fourth powers to appear somehow, we can multiply the first equation by x, the second by y, and the third by z to get this. Now we have the fourth powers in sight. All we need to do is add the three equations. Doing that gives us this. This is super convenient because we already know what this, and this are. So we'll just substitute those values in. After a little simplifying and rearranging, we get our answer. X to the fourth plus y to the fourth plus z to the fourth equals 25 over 6.
Awesome, we solved the problem using some algebra and a little cleverness. But we're just touching the tip of the iceberg. Here's a new question, this time with 4 variables. It's a bit of a mouthful, so I won't bother reading out all the equations. If you're brave enough, give this problem a shot. Before we get our hands dirty, notice the similarities this problem has with the first one. Yet again, we're trying to find the sum of the fourth powers of the variables. Moreover, all the given equations are symmetric. Let's look at each one. For the first equation, it's as if for each variable, we took the product wxyz and split that variable from the product to make it a separate term. For instance, splitting w from wxyz gives w plus xyz. Splitting x from wxyz gives x plus wyz, and so on. Since we did the same procedure to each input variable to form the expression, the equation is symmetric. The second equation is symmetric because it's as if for each variable, we squared it, then multiplied by all the other variables, then added everything together. It's a little trickier to see why the third equation is symmetric, but you can think of it like this. Using the 4 variables w, x, y, and z, there are 6 different possible pairs: wx, wy, wz, xy, xz, and yz. To form the expression, we squared every pair, then multiplied by the 2 variables that don't appear in the pair, and added everything together. As for the fourth equation, I leave that to you to convince yourself that it's symmetric.
Okay, hopefully you're convinced all the equations are symmetric. What's the next step? Well, when we were solving the first problem, we did a ton of nasty algebra to derive a polynomial that all the variables were a root of. I really don't want to do that again, especially since these equations seem more complicated than the ones we had before. But it would still be useful to have a nice polynomial that w, x, y, and z were all roots of, since you could apply the same trick as before to figure out what the sum of the fourth powers is. Maybe there's another way to get the polynomial without going through the nasty algebra. Well, if we want a polynomial p of t such that p of w, p of x, p of y, and p of z are all 0, the simplest thing we can do is let p of t equal t minus w times t minus x times t minus y times t minus z. If you plug any of w, x, y, or z into this polynomial, one of the factors is 0, so the entire product collapses to 0.
That's great and all, but if we're going to use the same trick we used before to find the sum of the fourth powers, we need p of t to look more like this. So let's multiply the product out. Since p is a fourth degree polynomial, when we multiply it out, we're going to have something times t to the fourth, plus something times t cubed, plus something times t squared, plus something times t, plus some constant. Let's reason about what each something has to be. The first one is easy. There's only one t to the fourth term that appears when we multiply out the product. We have to take a t from every factor. So the coefficient on t to the fourth is just 1. Now, how do we get t cubed terms in the product? We could take a minus w from the first factor and a t from the last 3 factors to get minus wt cubed. Or we could take these to get minus xt cubed, or these, and those are the only way to get a t cubed term. So in total, we have minus w plus x plus y plus z t cubed. Now for the t squared terms. We get a t squared term whenever we take a t from exactly 2 of the factors. Hence, we'll have a t squared term for every pair formed by the 4 constants w, x, y, and z. So the coefficient of t squared is wx plus wy plus wz plus xy plus xz plus yz. What about the linear terms? Those occur whenever we don't have one of w, x, y, or z. So the coefficient is minus xyz plus wyz plus wxz plus wxy. last but not least, the constant term. There's only one way to get a term without any t's, and that's by multiplying all of w, x, y, and z together to get w, x, y, z.
Now, this equation is a bit of a mess, so let's simplify it by introducing some notation. Let S1 be the sum of the constants, w plus x plus y plus z. Let S2 be the sum of all possible pairs of constants, wx plus wy plus wz plus xy plus xz plus yz. Let S3 be the sum of all possible triplets of constants, xyz plus wyz plus wxz plus wxy. Finally, let S4 be the product of all four constants, wxyz, which is the same as the sum of all possible quadruplets. We can now rewrite p of t as p of t equals t to the fourth minus s1t cubed plus s2t squared minus s3t plus s4. So the question is there a way we can use the given equations to figure out these coefficients?
I hope you noticed the similarities between S1, S2, S3, S4, and the given equations. For instance, in the first equation, the first four terms constitute S1, and the next four terms constitute S3. So we have S1 plus S3 equals minus 1. If we factor out wxyz from the second equation, it turns into S1 times S4 equals 1. Similarly, in the third equation, if we factor out wxyz, the first factor is S2, and the second factor is S4, so S2 times S4 equals 2. And the last equation is just S3 times S4 equals 3. Now, this is a much simpler system of four equations and four variables, so we can easily solve it. Adding the second and fourth equations gives S1s4 plus S3s4 equals 4. Then, we can factor out the S4 and replace S1 plus S3 with minus 1. Hence, S4 equals minus 4. Lastly, we can replace S4 with minus 4 in all the equations to get S1 equals minus a fourth, S2 equals minus 2 fourths, and S3 equals minus 3 fourths. Phew, we solved for S1, S2, S3, and S4, so we can plug these values into p of t to get p of t equals t to the fourth plus a fourth t cubed minus 2 fourths t squared plus 3 fourths t minus 4. And, because we specifically constructed p of t so that w, x, y, and z are all roots, these four equations must be true. Neat.
Let's multiply everything by 4 to clear the denominators. Since we want to find the sum w to the fourth plus x to the fourth plus y to the fourth plus z to the fourth, we can just add the equations. This gives us 4 times the sum of the fourth powers, plus the sum of the cubes, minus twice the sum of the squares, plus triple the sum, minus 64 equals 0. But this is an issue because we don't know what these sums are. If you remember back to when we solved the first problem, we knew what the sum of the cubes, the sum of the squares, and the sum of the variables were directly from the given equations. Unfortunately, in this problem, the given equations don't tell us that. But all hope isn't lost. I mean, we already know what w plus x plus y plus z is. That's S1, which is minus a fourth. Let's substitute that in. Now let's tackle the sum of the squares. It'd be nice if that were just S1 squared, but that's not how algebra works. Well, what is S1 squared? It can't be too far off from the sum of the squares, right? If we multiply it out, we get this. There's our target, the sum of the squares, but we also have this extra bit, wx plus wy plus wz plus xy plus xz plus yz. Do you see it? That's S2. So S1 squared equals w squared plus x squared plus y squared plus z squared plus 2s2. Now we can rearrange and plug in the fact that S1 is minus a fourth and S2 is minus 2 fourths, and we get that the sum of the squares is 17 over 16. Great, let's substitute that into our equation.
All that's left is the sum of the cubes. Maybe we can try the same trick we did to get the sum of the squares. We'll start by cubing S1. Instead of mechanically multiplying out this mess, let's think about what sort of terms we'll get. First and foremost, we'll have the cubes, w cubed plus x cubed plus y cubed plus z cubed. Next, we'll have terms that are the square of one variable times a different variable. For instance, the term w squared x occurs 3 times. Here are all 12 different variants of that. Finally, we'll have terms that are the product of 3 distinct variables. For instance, the term xyz occurs 6 times. Here are all 4 different variants of that. Now, this looks like a mess, but we can already relate it to some familiar things. We have the sum of the cubes here, which is what we want to solve for, and down here we have S3. The only thing left to deal with is this collection of terms in the middle. It looks a lot like S2, with every pair of variables occurring, but one of the variables is squared, which is the issue. Maybe we can multiply S2 with something to get terms that look like those. Let's try multiplying S2 with S1. When we expand it out, sometimes the variable from the first factor is the same as one of the variables from the second factor, so they make a square. But other times, none of the variables overlap, and we get a term like xyz. This term occurs 3 times, and here are all the different variants of it.
Okay, I promise we're almost done. Here's the big expression we wanted to solve for, and this piece is just S3. Let's rearrange and plug in the numbers. Voila! We'll now take this 19 over 8 and substitute it in over here. Now we'll plug in the numbers for S1 and S3, and we're just doing the arithmetic here. The sum of the cubes is minus 169 over 64. Unraveling the last layer, we plug this in up here. And after some more arithmetic, drumroll please, w to the fourth plus x to the fourth plus y to the fourth plus z to the fourth is 4449 over 256, or 17.3789065.
Awesome! We solved another crazy system of equations. But I promised in the video introduction to prove a beautiful theorem for you. This theorem has actually been operating covertly all along. Did you notice that in the last problem, once we found the values of S1, S2, S3, and S4, we could figure out everything else we needed from just those? We were able to completely forget about the given equations. For instance, we saw that w squared plus x squared plus y squared plus z squared is just s1 squared minus 2s2. And this massive mess was just s1, s2 minus 3s3. The fact that S1, S2, S3, and S4 alone could form those expressions is no coincidence. In fact, the S's can form any polynomial expression involving w, x, y, and z as long as it's symmetric. Since S1, S2, S3, and S4 are so special, they have a name. They're called the elementary symmetric polynomials in 4 variables.
Now, so far, we've just been working in the context of 4 variables, w, x, y, and z. So we had 4 elementary symmetric polynomials. We can extend to any number of variables like this. Suppose we have n variables, x1 through xn. The corresponding elementary symmetric polynomials in n variables would be s1, the sum of the variables, s2, the sum of all possible pairs of variables, and note that something like x1, x2 is the same as x2, x1, so we don't add it twice. S3, the sum of all possible triplets of variables, S4, the sum of all possible quadruplets of variables, and so on, all the way until Sn, the sum of all possible n tuples of variables, which is just the product x1, x2 to xn. The fundamental theorem of symmetric polynomials, that fancy theorem I mentioned at the beginning, says that any polynomial involving x1 through xn, that is, any expression formed by any combination of adding, subtracting, and multiplying together the x's and numbers, as long as it's symmetric, can be written solely in terms of the elementary symmetric polynomials, s1, s2 through sn. We already saw several examples of this theorem at work when we were solving the last system of equations. It's time to prove it in general.
Let's start with a little organization. Given a symmetric polynomial, we want to write it in some standardized form so it's easier to deal with. The standard form can be found by first, multiplying everything out and combining like terms, and second, ordering the terms according to their exponents. I'll show these steps with an example. The example I use will just be with 4 variables, x1, x2, x3, and x4, but the exact same logic applies no matter how many variables there are. Suppose we want to write the polynomial x1, x2 minus x3, x4 all squared times x1, x3 minus x2, x4 all squared times x1, x4 minus x2, x3 all squared in standard form. The first step is multiplying everything out and combining like terms, and if you do that carefully, you get this. Second, we want to order the terms according to their exponents. We'll start by fixing the notation, so let's insert any missing variables with an exponent of 0 and put an exponent of 1 on variables that don't have an exponent. Now, we can make a unique identifier for each term by just concatenating the exponents into a 4-digit number, called the multidegree of that term. Then, we order the terms based on their multidegree. This one has multidegree 0444, which is the smallest of them, so it'll be the first term in the standard form. Next, this one over here has multidegree 1335, then 1353, and so on. Boom, that's our standard form.
Now, what if we wanted to write this polynomial in terms of the elementary symmetric polynomials? To simplify things, let's forget about all this junk and start by focusing on the very last term, the term with the largest multidegree. Can we generate this term using some combination of the elementary symmetric polynomials? Here's one idea. Since we need x1 to the 6th power, let's take s1 and raise it to the 6th. Then, since we need x2, x3, and x4 all squared, let's take s3, which has the term x2, x3, x4, and square it. If we were to expand s1 to the 6th times s3 squared, one of the terms would be this one. Thus, by subtracting it from our polynomial, we'd be getting rid of the highest multi-degree term. But there's an issue with this approach. We're trying to simplify, but the expansion of s1 to the 6th times s3 squared contains many complicated terms other than the one we're trying to get at. The main issue is that it introduces terms with multi-degree larger than 6222. For instance, the term x1 to the 8th times x2 squared times x3 squared shows up in the expansion, which has a multi-degree of 8220. We want a procedure where we can get rid of the term with the largest multi-degree without introducing any new terms with even larger multi-degree. Can you think of a new way of multiplying together the elementary symmetric polynomials so that this term appears, and no terms with multi-degree higher than 6222 appear? Pause and give it a shot. As a hint, note that when you multiply two polynomials together, the term with the highest multi-degree in the product is the product of the terms with the highest multi-degree in each factor.
Here's the solution. We need the exponent on x1 to be 4 higher than the exponent on x2. If you were to raise s2, s3, or s4 to any power, the highest multi-degree term in the expansion would put the same exponent on x1 and x2. Thus, the only way to account for the difference in their exponents is by using s1. This means we should raise s1 to the 4th power. The highest multi-degree term in this expansion is x1 to the 4th, which needs to be multiplied by x1 squared times x2 squared times x3 squared times x4 squared to get the desired term. That's exactly s4 squared, so we should use s1 to the 4th times s4 squared. If that didn't make sense, just see for yourself. If you expand it, the term x1 to the 6th, x2 squared, x3 squared, x4 squared appears. And there's no way to get a term with higher multi-degree because the only term where the exponent on x1 is 6 is the term in question. This means that if we subtract s1 to the 4th times s4 squared from our original polynomial, we'll cancel out the term with multi-degree 6222. And because this term had the highest multi-degree in both our original polynomial and the expansion of s1 to the 4th times s4 squared, all the terms in this new polynomial have multi-degree strictly less than 6222. We've effectively reduced the maximum multi-degree of our polynomial. So let's repeat the process. Write this new polynomial in standard form, then figure out a way to get rid of the term with highest multi-degree by subtracting off a product of elementary symmetric polynomials. Then do it again and again and again. Since the highest multi-degree is strictly decreasing at each step, eventually the only term left will be a term with multi-degree 0000, which is just a constant. Now we simply rearrange things, and just like that, we have an expression for our original polynomial in terms of the elementary symmetric polynomials. All that's left to do is figure out what these question marks should be based on the term we're trying to eliminate at each step.
So let's say we're at a point in the process where the highest multi-degree term, the term we're trying to get rid of, is a times x1 to the d1 times x2 to the d2 times x3 to the d3 times x4 to the d4, where a is just some constant out front, and d1, d2, d3, and d4 are the exponents on each variable. What product of elementary symmetric polynomials and constants would generate this term, but not generate any terms of higher multi-degree? Before digging into this problem, notice that the exponents must be in decreasing order. d1 is at least d2, which is at least d3, which is at least d4. To prove it, suppose the term with the highest multi-degree was something like this, violating the decreasing order because this 3 is larger than this 1. Since the polynomial is symmetric, there must be a term where x3 is swapped with x4. But if we rewrite this term so that the variables appear in the proper order, we see that the multi-degree of this other term is larger than the multi-degree of our original term, contradicting the assumption that it had the highest multi-degree. Hence, the exponents must be in decreasing order. Okay, with that observation out of the way, pause and give the problem a try. What should these question marks be? It may be worth trying some concrete examples if you get stuck.
This one was pretty tough, but here's the answer. The difference between the exponent on x1 and the exponent on x2 can only be accounted for by s1, since the highest multi-degree terms in all the other elementary symmetric polynomials put the same exponent on x1 and x2. Thus, s1 should be raised to the d1 minus d2, which is at least 0 because the d's are in decreasing order. Now that we've chosen the exponent on s1, the difference between d2 and d3 can only be accounted for by s2, because the highest multi-degree term in both S3 and S4 puts the same exponent on x2 and x3. So S2 should be raised to the d2 minus d3. Continuing this logic, S3 should be raised to the d3 minus d4. Finally, to figure out the exponent on S4, note that x4 doesn't appear at all in the highest multi-degree term so far. So to get x4 to the d4, we need s4 to the d4. To make the constants match up, the constant out front should also be a. If you're not convinced, let's double check. If we were to expand this out, the highest multi-degree term would be the product of the highest multi-degree terms in all the factors, which is a times x1 to the d1 minus d2 times x1 x2 to the d2 minus d3 times x1 x2 x3 to the d3 minus d4 times x1 x2 x3 x4 to the d4. Rearranging and adding the appropriate exponents, we get a times x1 to the d1 minus d2 plus d2 minus d3 plus d3 minus d4 plus d4 times x2 to the d2 minus d3 plus d3 minus d4 plus d4 times x3 to the d3 minus d4 plus d4 times x4 to the d4, which is exactly a times x1 to the d1 times x2 to the d2 times x3 to the d3 times x4 to the d4, the term we wanted to get rid of.
And that's it! We have a procedure to write any symmetric polynomial in terms of just the elementary symmetric polynomials. To recap, we start with a symmetric polynomial, p of x1 to xn. We write p in standard form, and identify the term with highest multidegree. Say it's ax1 to the d1 through xn to the dn. Then we subtract off a times s1 to the d1 minus d2 times s2 to the d2 minus d3 through sn minus 1 to the dn minus 1 minus dn times sn to the dn, from p to cancel out the term. We repeat this process with the new polynomial, writing it in standard form, identifying the new highest multidegree term, and subtracting another product of elementary symmetric polynomials. We keep doing this until we're just left with a constant, at which point we have our solution.
If you made it this far, congratulations. We covered a ton of stuff. We started by solving an innocuous-looking question that led us down an algebraic rabbit hole. We then used what we learned from that solution to solve a second, even crazier-looking problem. Finally, we made the observation that the elementary symmetric polynomials could be used to form any symmetric expression we needed, and we turned that observation into a theorem with a rigorous proof. Learning anything new in math is hard, so to help digest everything we've covered, I've left some more problems on screen. The first few are calculation-based to practice the new equation-solving techniques you learned, and the next few introduce more depth into what we've covered. If you solve any of these, drop a solution in the comments.
We'd like to thank everyone for the incredible support we received. It's really what motivated us to make this video. If you have any comments or critiques though, let us know in the comment section.
If you haven't seen the video we made last year, What's so natural about the number e, we've linked it in the description, so go check it out.
Well, I think we've said everything that needs to be said, right?
Wait a minute. What's that?
Oh!